A cracked clay tablet sat ignored for a century until AI read it like a code. What looked like a dusty list of numbers turned out to be a message from 1800 BC, written in wedge marks so precise they shouldn't exist. You'll see how a palm-sized artifact, Plimpton 322, rewrites math history and exposes a system of power older and colder than we imagined. Archival trails, field tablets, and exact ratios decoded by modern AI. We'll trace the discovery, decode the numbers, reveal their uses, follow the researcher who connected the dots, and confront why the why is the most chilling part. From dust to dread. At first glance, Plimpton 322 looks ordinary, even dull. A palm-sized rectangle of cracked clay, its surface faded by millennia in the earth, it could easily be mistaken for a fragment of an ancient shopping list. And for decades, that is precisely how scholars treated it. Dug up in Mesopotamia in the early 1900s, the tablet passed quietly through the hands of a roguish archaeologist named Edgar Banks, a man whose flair for adventure later inspired the fictional Indiana Jones. Banks sold the artifact to a wealthy New York publisher named George Arthur Plimpton, who collected rare educational curiosities. After Plimpton's death, the clay piece was donated to Columbia University and tucked away in the mathematics department. There it sat, locked behind glass, catalogued with the sterile label Plimpton 322. No fanfare, no mystery, just another relic in a growing archive. For most visitors, it was little more than a curiosity, a lump of clay that seemed far too humble to matter. Strange stares were drawn toward the tablet even in those early years. Some scholars noted the jagged left-hand edge, where a section of clay had broken away. The breakage looked almost unnatural, as if that corner had been deliberately torn off. Was it the wear of time, or at some point, had something intentional happened? That broken edge would later trouble the minds of researchers and fuel the speculation that this tablet is only part of a larger, more complete work. If that is true, then this missing portion may have contained the very instructions to decipher the rest of the tablet's secrets. The festive style survived 4 columns and 15 rows of wedge-shaped markings, cuneiform numbers in Babylon's base 60 system. To an untutored gaze, these look like any other list tallies for goods, grain delivery, or trade exchange. But they had a problem. The numbers were too huge, outstripping any reasonable estimate for numbers of sheep, barley, or silver. They were not round estimates. Instead, they were very precise, deliberate, and somehow strangely ordered. The consensus among academics for years was indifference. Some claimed it was a merchant's ledger, others proposed it was a math exercise for the scribe. The most charitable interpretation entailed the consideration that it might have been a teaching tool. However, this, too, does not help explain the precision. Lacking context, the observations were stalled in the lecturing system, while the tablet stood gathering dust. Generations of students marched past the display case, oblivious to the existence of something so extraordinary that it was just an inch away. The disquiet persisted. What made the numbers so cleanly arranged? Why was each row supposed to stand in connection with the next? And what was on the edge of something now lost? Such questions flickered at the edges of scholarly articles but could never find their way into more mainstream ones. For most historians, then, Plimpton 322 remained a misfit, an artifact recognized but not understood. The great irony is that the most significant clue was staring right into their eyes. The sequence of numbers was too precise to be random. It was almost as if the tablet held a code waiting for the right kind of tools to discover its pattern. Only in this age of digital imaging and artificial intelligence, that pattern finally came to light, and it would be quite a shocking revelation. This was something other than just a ledger or an exercise, it was something much farther advanced. The odd part wasn't the clay, it was the pattern that refused to be ordinary. Numbers that shouldn't exist. When modern scholars began looking more closely at Plimpton 322, they realized the numbers on its surface weren't random at all. They weren't lists of goods, nor the results of routine bookkeeping. They followed a precise mathematical pattern, one so clean it seemed impossible for a civilization as ancient as Babylon to have produced it. The tablet records sets of 3 numbers. To a modern eye trained in geometry, they are instantly recognizable, Pythagorean triples. These are whole number sets that satisfy the equation most of us learn in school, a squared plus b squared equals c squared. The classic classroom example is the 3-4-5 triangle, where 3 squared plus 4 squared equals 5 squared. But Plimpton 322 didn't stop at simple, small sets. It listed enormous triples with flawless accuracy. There are some examples. The most striking is the fourth row, where the numbers are 12,709, 13,500, and 18,541. Squared and checked, they do fit perfectly into the equation. Not rounded, not approximate, all exact in just real numbers unmatched in the precision by the outside world, like a solved puzzle. Whoever engraved these numbers in clay was not just tossing in theories, they understood how right angles connected with each other, with an understanding not at all supposed until more than a millennium later. As much as the history of mathematics has been taught, there would be a theorem discovered in Greece in the 6th century before the Common Era. It was Pythagoras himself, the philosopher and mathematician, who gave it its final form. What is surprising, however, is to find it here inscribed in Babylonian clay tablets dated to about 1800 BC, thus proving that the Babylonians had possessed this principle many centuries before Pythagoras was ever born. These implications are indeed enormous. It is not a matter of coincidence or chance. The tablet displays not one or two isolated instances of right-angled triangles, it shows an explicit series, each row progressing from steep ratios to shallow ones in a very systematic way, as though it is a reference chart. Such ordering suggests practical use and not mere theoretical musings. It was a tool aimed at being consulted, not merely something to be gazed at. Equally important is the numerical system involved. The Babylonians worked in base 60, such is the sexagesimal system. Unlike our base 10 decimal, base 60 divides neatly into a whole bunch of factors. That meant fractions could be expressed extremely accurately, without all the hassle associated with rounding out in contemporary mathematics. Almost as stunning to modern scholars as were the triples was the realization that in many cases, the Babylonian system was not just advanced, it was superior to the Greek trigonometry that would be. Even more troubling to scholars was the lack of errors. Old records usually exhibit a few small imperfections, some corrections or inconsistencies, indicating that writing was done manually and adjustments were made. There isn't any mistake left on Plimpton 322. Each row, each number is perfect, as though copied from a perfectly established system. This was not the work in progress of a civilization that was still getting itself to come to terms with advanced mathematics. For centuries, the broken edge of the tablet has been taunting academia. But survive the numbers, and the tale alone changed reality for a long time. If Babylon had a more accurate trigonometry than Greece, the rewrite is quite different from history itself. The troubling questioning became clearer. What else had they known that we had forgotten? If the math is perfect, the better question is who needed perfection and for what?